So as I was saying, we have an analytical algebraic solution, but here we'll be using an iterative method to solve that problem, what we call the gradient descent or gradient ascent. These are objective functions, so we want to minimize the error, the best beta 1 and beta 0 that actually minimizes this error function. So when we are minimizing, it's called gradient descent, and when we are maximizing, that's called gradient ascent. So I take a negative of ascent. That means that is an equivalent to gradient descent. Okay. So let's talk a little bit about the general idea, and we are actually taking one specific function. This is a quadratic convex function. The convex function, you can think it as you are just climbing a mountain or a hill, that has this kind of shape. And one thing you need to track as per the gradient descent learning is that you can think a way that you are actually building some stairs to climb up to the mountain, and there is one rule: your stair width should be same, and your stair height will cut off the periphery of the mountain. This will give you the direction of your movement, just like you are climbing on top of the mountain. So you are keeping track of, if I have a step something like this, then what is my step height, So step width, height, just like your stairs, And that is actually represented by this derivative function. For those who have no knowledge about calculus, just think it as you are climbing on top of the mountain and you are keeping track of stairs height, And when you can say that, I am on top of the mountain, where you will see very tiny height stairs. That means you are on the flat surface, Two things to remember: that things actually depend on like your step size and what we will call as learning rate. That has a dependency on this step size, So think it in this way. So if you take a step size bigger than the mountain width, so what will happen? You will miss mountain, right? So if you take a bigger step, something like here, up to here, then you'll miss the mountain top. On the contrary, if you take a smaller step size, then you will have to build many steps, So that's the relationship between the step size and whether you miss the top of the mountain or you take more time to climb up the mountain, So now go to the original problem and the algorithm, so you will understand quickly. Our objective function, if you recall, is this one, We are minimizing the error function. Our theta has two parameters, beta 0 and beta 1. So you are actually minimizing negative convex and, as I was saying, opposite direction of your maximization problem. So in a summary, you have to apply the same rule here, but now you are actually exploring your parameter space in a two-dimensional space, beta 0 and beta 1. And the algorithm looks something like this. So you start with an initial beta 0 and beta 1, and you select a learning rate. Learning rate means your step size, and you estimate your loss, and you estimate the derivative. Then you will know that which direction you need to move, And here you do a partial derivative. Partial derivative means that you take a derivative per parameter, So here, although this error function is a function of two variables, beta 0 and beta 1, but I am estimating the derivative for beta 0, another derivative for beta 1, for the same error function. You know your initial beta 0, you have a learning rate, and you got your derivative. So if you apply this rule, you will get a new beta 0 and beta 1. Let's say you started something here, then you will get to the next point that you need to move, So you got a new beta 0 and beta 1, and you iterate the process, where up to when? Up to the point, So all these derivatives are actually getting close to 0. Or if you think that, I just want to run for, let's say, a number of iterations, then you can just stop there. So in summary, you start with the initial beta 0, beta 1. You fix a learning rate. you estimate your error, you take the partial derivative, and you update each of your parameters. And then you iterate over the process n number of times. Or when you find that the derivatives actually are not changing, okay? So this is all about gradient descent algorithm. Okay, let's go to the corresponding notebook presentation. I have already shared this notebook through Blackboard, and also you'll find this on my GitHub repo. So first I'm loading the required packages, NumPy, Pandas, and Plotly. And I wrote a class that will generate some linear data with random white noise being added, okay? When I show the data, you will quickly be able to connect, okay? In the next class, I'm implementing the linear regression using gradient, okay, that we have just explained. I have encoded the beta 1 variable as slope and then beta 0 as intercept, just like what we have shown in the presentation. And now the whole idea is that we'll generate some data points, so here I am asking 100 data points, and we'll give an random input, intercept parameter, the beta 0 to be 6 and then slope to be -5. The data is looking something like this. You can play with anything, like for example changing the slope to positive is generating the data on the upward direction, okay? So nothing crazy. Then what we want to do, we want to test this gradient descent algorithm. As we have seen in the algorithm, that we have to start with a random beta 0 and beta 1. So this is my random starting point, -12 and -18, but you can give any number, so for example let's take -1, okay, and -8, okay. And I see that the algorithm went quite fast. We started here 0 0, but the solution came here. But let's take less examples. So we do the same. So the graph shows that I started here as my initial model, the location -1 for the intercept and -8 for the slope, The starting model was looking like this, and after 99 iteration, the model was able to find the pattern. I do this one 8 and let's do this one 10. So again, you see, like we started here, and then the model was able to find the solution, close enough. So feel free to play with the solution. This will give some understanding of what's happening. So okay, thank you.